Previously, when we talked about gravitational potential energy, we defined it in this way. We said that if I take an object and I raise it up a height h, we raise it up a height h from the ground, and if I define the gravitational potential energy on the ground as being 0, which is like the surface of the Earth, then the gravitational potential energy that the object would have if it has a mass m and is a height h above the ground would be equal to m times g times h if the strength of the gravitational field is g. And this works as long as we're close to the surface of the Earth and our changes in height are not very big. But let's say now that this circle I'm drawing is the Earth, and I'm at a point that's way out here. So a distance that is even much larger than the radius of the planet itself. I could say now that I'm a distance r away from the center of that planet, and that distance r is much bigger than the radius of the Earth. Once we start to have big changes in r, or we get far away from the center of the planet, then the gravitational field, lowercase g, is no longer constant. And so we can't say that the gravitational potential energy that that object has at that point, I'll label that point P, the gravitational potential energy at point P is not equal to mgh. And while the way we'll have to define the gravitational potential energy for cases like at point P or further away is a little bit tough, I'm going to show a few of the steps that will help us understand why we have the equation that we will have for gravitational potential energy in these cases. For cases where the distance from to the center of the planet is quite large, we will define the gravitational potential energy, Ug, to be equal to 0 when the point we're at is an infinite distance away from the center of that planet. And so when the distance we are away from the center of that planet is equal to infinity, then the gravitational potential energy is defined as 0 at that point. When we are close to the surface of the Earth, we have the choice to define the place where h equals 0, but when we're further away, we're going to not have a choice. We're going to say that the gravitational potential energy is equal to 0 at an infinite distance away. And what we should realize is that the further I move away from this planet, the gravitational potential energy should be increasing more and more and more. And so I guess we could say that as r increases, then we should expect that the gravitational potential energy also increases. And so if the gravitational potential energy is defined as 0 at an infinite distance away, then as I move closer to the planet, the gravitational potential energy should be negative. So that as I move further away from the planet, the gravitational potential energy is less negative, and it's increasing with increasing r. The equation for the gravitational potential energy at any point away from a large mass is equal to minus negative value, the universal gravitational constant, capital letter G, the mass of the object times the mass of the planet or the star, divided by the distance between the two, r. And so what we find is that the gravitational potential energy, in this case, is proportional to 1 over r. The last thing that I would like to do is to make a graph of gravitational potential energy versus distance away from some object. If we were to graph this 1 over r function on these axes, then we would find that the graph looks something like this. And let's say that if we moved an object between 2 points, points A and B, and those 2 points, A and B, are a distance h apart. So the distance between points A and B is h. The change in gravitational potential energy, which is hard to see on the graph that I've drawn, but you should be able to notice that the gravitational potential energy at these 2 points would not be equal. If we could read these points off of the graph, then there would be a difference in gravitational potential at that point. And that difference in gravitational potential energy is not equal to mgh if points A and B are far apart and we're not near the surface of the Earth. The change in gravitational potential energy would not be equal to mgh. We would have to use the expression that we have here, minus g times m divided by r, to find that difference in gravitational potential energy. Another feature of the graph that I would like to point out is that as r increases more and more and more, we would be getting closer and closer to the place where the gravitational potential energy increases, but you should expect the graph to be asymptotic because we can never get to the place where ug equals 0, but we can get very close. This might feel kind of weird to define the gravitational potential energy as being negative and thinking of this as maybe some kind of negative energy, but really only changes in gravitational potential energy are what's important, and that as I move further away from an object, the gravitational potential energy should be increasing. And so if you look at the expression, as r increases, the magnitude of the potential energy will decrease. But since it's negative, and we have a number that is less negative, we're moving closer to 0, and so the gravitational potential energy is increasing. And really, if we wanted to, we could also just define the place where h equals 0 to be at a different location, even for places close to the surface of the Earth. And so, for example, in the picture that I've drawn on the left, if I were to define the gravitational potential energy, let's say at this height way up here as being the place where h is equal to 0, then the gravitational potential energy that that object has, that yellow dot has, at the location where I've drawn it, would already be a negative gravitational potential energy. And so there's no problem with defining energies as being negative as long as they're defined in a way that makes physical sense. And here, what that means for us is as we move further away from an object, the gravitational potential energy should increase, and using either definition, we have that condition met. But now we have expressions that can help us understand a problem regardless of how far away we are from a planet, even for cases where the gravitational acceleration might be changing on the scales that we're understanding the problem at.